Hello. In applications, we use differential equation to describe processes, or in another way, to describe behavior of some systems that we are interested in. And this differential equation, with a bit of luck, then helps us in understanding the situation. If we are really lucky, we can find a general solution. And then, as we saw, we can, for instance, use it to focus on a specific instance of a process. For instance, when we have an initial condition, like we have over here. But there is another interesting application. Looking at a general solution, we can try to generate a representative set of solutions. So you imagine many, many solutions drawn into one picture and chosen in such a way that they capture all possible developments of this process. So when you look at such a picture, you get a very good overview of what you can actually expect. Let me show you an example. One of the differential equations that we learned how to solve leads to the following picture. These are the solutions to differential equation that we saw in the first lecture on differential equations. And when we look at such a picture, we can see the development in time. And these are, let's say, states of some system, and we can see what's happening. We can see what are the choices, what are the options. We get a very good feeling for the behavior of the system when we see a picture like that. So this will be the focus for today, obtaining a picture like that for our differential equation. However, problem is that not always we are able to find the general solution. We found some procedures like separation or variation for linear equations. We also saw some other bonus tricks, if you looked at the bonus video. Unfortunately, only a relatively small portion of differential equations can be handled using these approaches. And many differential equations cannot be solved at all analytically. Here is a simple example. For instance, y prime is equal to y divided by y minus 1. That's a very nice differential equation. It looks very simple. There is no x on the right, for instance, so this looks really simple. And yet, there is no procedure which would provide us with a general solution. So this equation is not solvable analytically. And yet, we would really like to know how the system which it describes behaves. We would like to get a picture like that, or at least something similar. So how do we get it? The idea is that we look at the differential equation that we have, and we try to draw information from the equation itself. And we already actually did something like that, because when we see a differential equation, the first question is, okay, are there any limitations? So let's have a look at an example. Y prime is equal to 2x times y minus 1. That's actually the differential equation for which we have this picture. We look at it and we ask, are there any limitations? And the answer is no. So, in principle, solutions can exist anywhere in the real plane. So x and y could be anything. That's the conclusion of the first analysis of our equation. That was easy. Let's have a look at this example. Actually, I prefer to look at a slightly more difficult example, this one. Although, and it's an interesting paradox, this equation now can be actually solved analytically. But it will be more challenging for what we are doing right now, for the analysis. So I look at this equation and I ask, okay, what can go wrong? And the answer is, the obvious condition, y minus x should be different from 0. So typically we would actually ask what is forbidden. So I don't want y minus x to be 0, which actually describes the main diagonal in the plane. So here is a sketch. I have my usual xy plane, and in this xy plane the main diagonal is actually forbidden. No solution is allowed to touch it. So there may be some solutions over here, there may be some solutions over here in those, let's say, infinite triangles, but definitely no solution can actually cross the main diagonal. So this is already some sort of information. However, we want more. We want to know something about the way the solutions go as the time grows. We want to know how they pass from left to right. So we go back to our differential equation, to the general case, and when we look at it, we actually can see two different points of view connected in one picture. So here we go. Our basic xy plane When I look at the left-hand side of my differential equation, I can see the derivative of the solution. So in the left-hand side, I'm actually treating solution as a function. And if I draw a graph of this, I can see y as a dependent variable on x. So this is typical graph of a function, solution y. And if there is an initial condition, then it has a natural interpretation. At some time x0, the value should be y0. So that's the left-hand side of the differential equation. On the other hand, on the right-hand side, there is simply some expression with x and y. We can see it over here. We can see it over here. And when you look just at this expression, there is no hierarchy. I simply see two independent variables. So I can see this picture also as a picture of the xy plane with no hierarchy, two-dimensional place. And I can see some curves passing through this place, to this plane. And the initial condition can now be interpreted as a curve passing through a two-dimensional point. So on the right, I have information which is based on two-dimensional world. This is actually a function of two variables, and we have some tools for such functions. And this function of two variables provides information about my solution, depending on the location. When the solution passes through a certain point, then the right-hand side tells me something about, well, about its derivative. So this is an important interpretation, and it allows me to say something about my solutions, because what is derivative? Derivative is information about increase, decrease. So when I go and look at my example over here, I can see that the increase or decrease of the solution depends on some formula which has x and y as the inputting variables. So I can form a question that we know from calculus. Given some function, can I somehow determine where is it growing and where is it decreasing? That's a good question, and we know how to handle it in one variable case. We had this procedure where we first find the dividing points. We call them critical points. And if you remember, critical points can be recognized by derivative being 0 or not existing. And exactly the same thing will be happening here in the case of two variables. I have a function of two variables, which is providing me with the derivative. And I will have dividing curves, not points now, and they will be given by two possible cases. One case is when the derivative is 0, and the other case is when the derivative does not exist. These are the two possibilities. So, could it happen that the derivative does not exist? And the answer is no, it never happens. So this is not a source of interesting dividing curves. Okay, this is gone. Could it happen that the derivative is 0? And the answer is yes, the derivative is 0 if the first term is 0, because there is a product, very convenient. So one possibility is that x is 0. And the second possibility is that y minus 1 is 0. Now, when you have a function of one variable, it lives on a real line. And when we find dividing points using the derivative, they split the real line into segments. And on each segment, we then determine increase, decrease. Here, the right-hand side, the function f in our picture, lives in two dimensions. So when we ask about the derivative of the solution being 0 or not existing, we do not get points, but we get curves, dividing curves. X is equal to 0, that's a two-dimensional object. That's important now. This is not a point or a number, but it's an object in two dimensions. That's the key trick. Which object? X equal to 0, that's the y-axis. So let me emphasize it somehow like that y-axis is actually a dividing curve for my analysis. Here we have another dividing curve. Y minus 1 is equal to 0. This actually reads y is equal to 1. But again, I should be careful. This is not a point. That's a curve, two-dimensional curve. And it looks like this. These two dividing curves take our plane and divide it into parts. 1, 2, 3, 4 distinct parts. And just like with the functions of one variable, once you stay within one region like that, the sign of the derivative, or the sign of the right-hand side, which is the same thing, is no longer changing. So in all those places, the two-dimensional function has the same sign, and therefore also the derivative of the solutions that pass through here also have the same sign. Now, key question, what sign is it? Well, there is a very simple trick. All through this place, the sign of the right-hand side is the same, so I just pick some point and substitute. For instance, this one. It could be, I don't know, 1, 0, perhaps 1, 0. So I take the point 1, 0, and I substitute it here into my formula, and I get 2 times minus 1 is a negative number. I don't really care about the value, just about the sign. So here in the lower right corner, the sign is negative everywhere, because it's negative here, and the only dividing curves are these two. So there can be no change of sign happening over here. Everywhere here, the right-hand side as an expression is negative, and therefore, every time a solution passes through here, it must have negative derivative, and it must be decreasing. So all the solutions passing through here must be decreasing. I don't know how fast they go down, but they are decreasing. So that's the important information. Let's try it over here. Okay, here the level is 1, y is equal to 1. So if I want to go into the upper right corner, I have to go still higher. So this point could be, let's say, 1, 2. I take 1, 2, and I substitute 1 for x, 2 for y. I get a positive number. So in this region, the solutions are increasing. Let's move on. Over here, I pick a point, let's say negative 1, 2. Should I write it? Okay, let me put it here. Negative 1, 2. Negative 1 for x, 2 for y. This gives me a negative sign. So the solutions here are decreasing. Now the important trick or important thing to remember, when we are interpreting solutions, the x-axis stands for time, intuitively. So we are always moving left to right. So when we are saying decreasing solutions, we want to see the arrows going left to right in this way. What we do not want to see over here in this region, or in this region, is an arrow that goes like that. The slope looks the same, but the interpretation is different. This sends a bad message, okay? So we always go left to right. Okay, I don't want to see it anymore. Okay, it's gone. It's never been here. Okay, the last corner. You can try it for yourself. Pick a point, substitute, you get plus. So the solutions here are increasing. What I just did is called sketching the slope field, or sketching the vector field. Let's see. We actually have some graphs over here. We actually have only the right half plane. So we are looking at the picture from the y-axis to the right. Decreasing, increasing. Is it true? Yeah, it fits. Decreasing, increasing. So you can see, even if I couldn't solve this problem, let's say that I forget how to do separation, I could still, just by analyzing the signs of the right-hand side, get some information about the shape of the solutions. Let's try it here. This will be a little bit more challenging. So I have my derivative of the solutions here expressed as an expression of two variables. Could it happen that the derivative is actually 0? That's a good question. Could it happen that the derivative actually does not exist? Another good question. Okay, the derivative can be 0 if y is 0. And again, I have to treat this as a two-dimensional object. Y is equal to 0. That's the x-axis. So here is my dividing curve. Over here, it actually coincides with the x-axis. Perhaps a colored chalk would be better, but it's hard to see on the recording anyway, so let's do it like that. Okay, could it happen that the derivative does not exist? Well, of course, it does not exist where there are no solutions over here. So we could say that there is no solution, so it's not really valid possibility. But since we are looking at dividing curves, it is a good idea to incorporate it. So here, the outcome of this question, could it happen that derivative does not exist, is the curve y minus x is equal to 0. That's definitely something that allows for a change of sign. That's important. And again, I interpret it as a curve. Y is equal to x. So this gap here, this line which is removed from the picture, from the plane, is actually also a dividing curve. So we have two dividing curves, and they split the plane into 4 regions. One of them is here, another one here. So it's 2 triangles and 2 whatevers. Okay, some regions here. Now, what are the signs? And I can play the same game. Just here one has to be a little bit more careful. For instance, if I pick 0.11, it will be exactly on the dividing line. So that's useless. So I have to pick a point which is a little bit more to the right, let's say 2,1. That looks like a good idea. If I pick the point 2,1, that's 2 for x, 1 for y, I get a negative sign. So here, the sign is negative, and the solutions are decreasing. Okay. What's happening over here? Well, let's say that I put x for x equal to 0 and y equal to my favorite number 13. So when y is 13 and x is 0, I'm getting positive sign. So positive sign applies to this whole region, whatever. Perhaps trapezoid could be a name for it, infinite trapezoid. And over here, the solutions are increasing. And I'm going to draw arrows in such a way that they somehow send the message that this whole region is just one unit, one object. Okay, then there is this little triangle. So I pick a point, let's say -2 for x and -1 for y, and I work it out. Okay, I have to be careful. Negative, negative, negative. So the solutions that pass through here are all decreasing. And finally, there is this trapezoid and some nice point. Let's say 0 for x and -5 for y, I'm getting plus. So increasing here, increasing everywhere here. This looks actually quite interesting, because when a solution goes here, it's supposed to be going up. I can imagine this one. But over here, it's supposed to go up and then down. Is it possible somehow? Actually, that's quite tricky. So this looks like an interesting phenomenon, or an interesting system, which is described by this equation. Okay, so again, this is what we call sketching the slope field. Now, there are 2 tricks that are useful, and I like to use them when I can. Generally, differential equations can come in many forms, but very often the right-hand side actually has a form of a product or a ratio. And in that case, you can actually investigate each factor separately. And this may simplify your life. So let's have a look at this example. How will it work? Okay. That's an alternative. First, I'm going to look at the factor 2x. So I ask, what is the dividing point or dividing curve for 2x? And the obvious answer is when x is equal to 0. That's the change of sign. X is equal to 0, that's this line, the y-axis. So the beginning is really the same as here, this general idea. But now comes a change. I look at the factor 2x, and I will ask about the sign of this factor depending on which side of the dividing curve I am. So when I'm to the right of my dividing curve, x is positive, and this factor is therefore positive. So I'll mark a little plus over here. When I'm to the left of my dividing curve, then x is negative, and this factor is negative. And I will mark a little minus here. Now let's pass to the second factor, y minus 1. When is it 0? Well, it's 0 when y is equal to 1. I have my dividing curve. Y is equal to 1, passing through 1. Okay, what do I know about the sign of this factor, y minus 1? Well, again, there are 2 parts of the plane. When I'm above my dividing curve, then y is really large, let's say infinity. That's a nice large y. I put infinity here and I can see positive. So above, the sign is positive. And below, quite naturally, let's say y is 0, the sign is negative. When I put it here, I can see it right away. So in this picture, I encoded my dividing curves, and for each curve, I also encoded its influence, or rather the influence of its factor. Factor to x, the influence is here. Factor y minus 1, the influence is here. Okay? Now, I can see 4 regions, and each region is hit by those 2 influences. So for instance, when I'm here in the upper right corner, this factor influences it in the positive way, and this factor influences it in the positive way. Plus times plus, because I'm multiplying here, give me plus. And I see increase. In the lower right corner, the horizontal dividing curve, which is the factor y minus 1, spreads here negative influence, whereas this dividing curve spreads the positive influence. Positive, negative gives me negative. And I am decreasing here. Negative, negative gives me plus. And negative, positive gives me minus. As you can see, this was actually easier because each time I had to worry only about a single factor. And then I just composed the signs easily, and I got the overall information about increase and decrease. So if your right-hand side in the equation has the form of a multiplication or a division, even there could be like 3 or 4 factors, you could try this approach. Actually, when there are more factors, things get a bit tricky, because then there will be more influences collating in individual regions, and it can get tricky. So for more complicated formulas, I actually prefer this approach, which is general. That's an approach which always works. So it's a bottom line approach. It's safe. But if you get lucky and if you have a nice differential equation, you can save time by using this trick. Let's try it over here. I can see 2 factors. So here is my basic xy plane. And in the numerator, I can see factor y. The dividing curve or dividing value for the factor y is this one. Y is equal to 0. What are the influences? When I'm above, y is infinity, I put it here and I get plus. When I'm below, y is negative and the factor is also negative. So far, so good. Okay, another factor, y minus x. What is the 0 point of this factor? The answer is it's the curve y minus x is equal to 0, which is y equal to x. So here is my second dividing curve. And this is where it gets a little bit more interesting. I have to figure out influences. So again, there are 2 parts of the plane created by this dividing curve. And if I'm over here, what is the sign of this factor by itself? That's a good question. And there are actually several approaches that you can use. You can pick a point and just substitute it here, or you can use the knowledge of graph sketching. For instance, we know that when I'm here above the curve, then y should be greater than x. If you are experienced with drawing graphs, things like that, this is easy to see. There are all kinds of things you can use. For instance, I may imagine that I'm traveling along the y-axis upwards, then x is 0, and y is becoming really huge. So here in this direction, the sign should be positive. Whereas when I'm moving down, x is 0 and y goes to negative infinity. 0, negative infinity, it's negative here, below this diagonal. Or if you want, you can go to this infinity. You can go to the right, then y is 0 and x is becoming really large. When y is 0, x is large, the whole thing, the whole factor is negative. So here, in this region, I get negative sign, okay? So again, I handled each factor separately, and now I just put the influences together. So in the triangle, plus minus gives me minus. In this trapezoid, plus plus yields plus. Minus plus yields minus. Minus minus, that means plus. And I draw the picture, and it works out really nice. Is it the same? Yes, it is. Okay. So for differential equations which have factors, things are very nice. I promised 3 tricks. So the first trick is the default procedure. You just find dividing curves, and for each resulting region you use substituting trick to determine the sign. The second trick, you go by factors. The third trick works for separable equations. This equation is separable. So what one can do, and I will show it in the next example because this one is already crowded, what you can do, you actually separate the influence of x and you separate the influence of y, and you treat them as independent problems, one-dimensional problems, and that's something that we know. So here I would treat the x part as an independent problem. The dividing point is 0. Now it's just a point because it's one-dimensional case, function of one variable. And I can easily find that for positive x's, the factor is positive. For negative, it's negative. And now I take this picture and transform it here, and the influence goes up. I will talk about it in detail a little bit more. Then I look at the y part, and again, I can treat it as a one-dimensional case. Here is y. The dividing point is 1. And again, I work out the signs just like I am used to in Calculus 1. And I take this information, that's y influence. Y influence goes in this direction. So that's the third approach. I will show a special example about it. Okay, so what we have here is the art called sketching the slope field. Now, when somebody asks you to sketch a dog, it's assumed that there is such a thing as a dog. So when I'm sketching a slope field, it implicitly says that there should be something which is called a slope field. So what's a slope field? Let's have a look at it again here. Do you remember how we determined the signs here? I was picking points and substituting. For instance, this point is 2, 1. And I took the point 2, 1 and I substituted into my equation. And what I got was 1 divided by negative 1, which is negative 1. And I said, okay, negative sign. But actually, I know that a solution which passes through this point has a slope negative 1. So the solution must be passing in this direction. And of course, when it moves away from this point, the slope will most likely change. But at this particular point, the slope is negative 1. Okay, how about, well, this point? I already have a mark here, point 0, 1. When I put 0 for x, 1 for y, the slope is 1. So the solution must pass in this way. And when x is 0, it's actually never there, and the slope is always 1. So also here and here, everywhere here, the slope is 1. Interesting. Let's try something else. Let's say over here. Negative 2, 1. In other words, I'm putting 1 for y, and negative 2 for x. Okay. So it's 1/3, okay? To be on the safe side. So here, at this particular point, when I substitute, I get 1/3. So the slope is not quite 45 degrees. It's a triangle 3 to 1. That's the proper slope, 3 to 1. So it should be like that. It's rather flat. Okay? Now imagine that I do this at many, many points. So I set up a regular grid, a square grid or rectangular grid. And for all points in this grid, I will simply substitute and I will sketch a corresponding segment which goes at a corresponding angle or slope. Notice that this is nothing, let's say, approximate. These are precise calculations. For every precise point, I'm substituting and getting precise information. So this is a nice, straightforward procedure, no guessing involved. And the result of this procedure is a picture with many, many, many segments, or rather arrows, and they should send me a very good message about the behavior of the system. And that's what is called slope field. So here, what you see is the slope field for this equation. And you can see that this decrease-increase is actually apparent here in this picture, but we are actually getting more information. because we are not just seeing increase, decrease, but also the rate of increase, the rate of decrease. And when you sort of mentally connect those arrows, you can sort of mentally see the solutions. Do you see them there? I can see little hills in the lower half, and in the upper half I can see pits, okay, dips. Let me add a few curves into the picture. So these are two actual solutions, and you can see how they follow the arrows, okay, they follow the slope field. So when you have an equation, differential equation, which you cannot solve, and you want to know what to expect from this system, what you can do, you just ask a computer to sketch the slope field, and you look at it, and you can start getting really good ideas about what you can expect from this system. Let me show you the slope field for this particular example. Here we go. So we can see the gap, that's the forbidden diagonal, and increase, decrease, increase, decrease. Everything works well. Okay, so these are really interesting arrows, especially in the lower left corner. It seems that as the solution grows, it could either curve to the right and continue, but perhaps if I start more to the left, it could go steeper and steeper up until it hits the diagonal and dies, because it's not allowed to go to the diagonal. So really interesting things happening. Again, I decided to draw some solutions. And you can see interesting types of behavior in this system. So that's very nice. On a test, I will definitely ask for a slope field, for the sketch of the slope field. So a picture like that, or like that, if you are lucky and you have factors and you know how to use the trick. I am not going to ask for the slope field because you are not computers. Okay? So that's the first and perhaps the most important topic of this lecture, the slope field. Let's take it a little bit farther, because there are some interesting questions still related to the behavior of the solutions. Okay? So let's have a look at the next example. Y prime is equal to 1 plus y times 1 minus y. That's a nice differential equation, and actually it's possible to solve it by separation because it's a separable equation. If I put times 1 here, then this becomes the x factor, and this part is the y factor. And now I could use the general procedure, and I could ask, okay, are there any points where the derivative does not exist, or perhaps where it is 0? Good questions, and it would go like that. Could it be 0? And the answer is yes, when y is 1 and y is negative 1. And again, I should see these as curves. Question number 2, I shouldn't forget. Is it possible that the derivative does not exist? And the answer is never. So that was easy. And then we would draw the two curves, y is equal to 1, y is equal to negative 1. Things would work out. What I'm going to do, I'm going to use the third approach, the one where I'm separating the influences of variables. So, first, the influence of the y variable. I just look at it as a function of one variable and I ask, what do I know about the sign? Because the sign, that's the key part. Well, that's a very simple one-dimensional problem. I just ask for 0 points, which are 1 and negative 1. And then I determine the signs here in my favorite way. Because it's itself, this y factor is itself a product of two factors. I can use the chart method or table method, looking at each factor separately, putting it together. Or I could use the substituting trick. For instance, here, when I put 0 for y, I get positive. When I put infinity for y, I get negative. And when I put negative infinity for y, I get negative. Okay? And I got my information. Wonderful. Now, I should also handle the x factor. I will do it in a second. Now comes the interesting part. When we are in the plane and asking about the sign, there are two influences. One is coming from the y term, the other one is coming from the x term. Now, the y term depends only on the y coordinate, which is a horizontal height or elevation of my point. So all the points on the same elevation, they get the same information from the y factor. So the y influence spreads in the horizontal direction. And therefore, it makes sense to sketch my resulting picture, this picture, for y, in a vertical way. See, it aligns nicely with the y-axis. And on this picture over here, I'm going to record my conclusions. So there are two dividing values, but now they become dividing curves because the influence spreads to the right. And here I'm going to copy the information about signs. Minus, plus, minus. So this influence spreads to the right throughout my picture. Now I'm going to do the same thing with the x factor. X factor consists of just constant, 1. So there is no change. It's always positive. So there is influence from the x-axis, which is always plus everywhere, and it spreads upwards. Because when you are sitting somewhere in the plane and asking, okay, what is the influence of the x factor, you are in fact looking downwards for the x coordinate. So the x influence spreads in the vertical direction. Now from the vertical direction, you've got pluses. This is a special case. I will talk about it in a second. Here, in this example, the x influence is actually split because on the right it's positive, on the left negative. See? So I should take this picture, transform it here. I would see plus here, minus here, and these two influences, they spread upwards. And I would get another picture, vertical picture over here for y. The dividing point is 1, and it's plus here, minus here, and this influence spreads horizontally. And these two influences, they meet, and they create exactly this little square of signs. In this example, situation is simpler, but at the same time more interesting by the absence of the x factor. It's not really here, so it does not influence the outcome. So in this horizontal strip, the derivative is always negative. It's given by the y factor. So I can see the minus sign here. Let me just draw some arrows. In the middle strip, the derivative is positive. And finally, in the lower strip, the derivative is negative. Okay? So that's how you handle influences of x variable and y variable if you can separate them. You just write down the information along the edges of your picture and you merge this information. You let them ooze into your picture. I am not aware of any name of this, and this is not like a general procedure that everybody would use. This is my specific approach, especially these little guys around here. So if you don't like doing that, I'm not forcing you. This is just like a bonus offer. Okay? Anyway, now here we have our sketch of the slope field. Now, this slope field is very special, and we can also see it in the derivative, in the differential equation. The derivative does not depend on the location with respect to the x position. Or in this picture, the information about the slope does not depend in the horizontal shift. If I shift my picture a little bit, the answer about the derivative will still be the same. And this essentially means that if you start your solution somewhere, or here, then these three solutions will go in the same way. This is a very specific situation. Equations like that, they are called autonomous. Let me put up a slide. So autonomous differential equations are equations where the free variable does not appear in the formula. And when you think about it, this is actually to be expected in applications. If you take some natural law, let's say the law of gravity, then the law does not care how you measure time. If I drop a chalk, it simply drops in a specific way, and the chalk does not care whether it's Monday or Tuesday. And the chalk does not care whether the government forces me to use the summer savings time or not. So it's quite natural to expect that in a differential equation which describes something real, something from our world, the time or position will not really play any role. So these autonomous equations, they are very typical. These two guys are not autonomous because there is x in the picture. Okay? So for equations like that, things are slightly different, and they're an inspiration to some interesting questions. But these questions are actually more general. So the first interesting exploration is this. When we look at the solutions, sometimes there are solutions that are very, very special. And very special solutions in particular are so-called stationary solutions. So let me put it here. What is the stationary solution? Well, stationary solution is a solution which describes a procedure which is stationary. In other words, it does not change. So, mathematically speaking, a stationary solution is a solution which is constant, a constant function for every x from some interval. For instance, when we solved this equation, we actually found that one of the solutions is the constant function y is equal to 1. That's a solution, and it's been over here. Let me see. Let me go back to Maple, and when we look up here, there is one solution, y is equal to 1. That's one of them. That's a stationary solution. Let me put it here. Stationary solution. Yx is equal to 1 for x belonging to real numbers. Okay? We actually talk about stationary solutions when we are talking about separation, but that's a much more general notion. It's not related to separation, in fact, but to the idea that sometimes a constant function solves my differential equation. Now, the nice thing is that I can say whether there is a stationary solution or not just by looking at the equation. What does it mean that a constant function solves my differential equation? Well, the derivative of such a solution is always 0, and therefore the solution, the stationary solution, if I put it into the right-hand side, also must be always 0, regardless of time, regardless of x. So the test for stationary solution is that the value y0 must satisfy the following equation. Fx y0 is equal to 0 for every x. So when I want to know whether there are some stationary solutions or not, I simply look at my equation at the right-hand side and I ask myself, is it possible to find a specific value for y, which, if I put in, I will get 0 regardless of x? Is it possible? And the answer is, well, of course, yes. I can see it over here. So when we are sketching the slope field, we are in fact also talking a little bit about stationary solutions because they are included among the dividing curves. Over here, I can see two stationary solutions. If I put 1 for y, then the right-hand side becomes 0 regardless of x. Well, there is no x anyway, so the autonomous differential equations, they are really good for stationary solutions. But as I said, this is a more general notion. So let me put here two stationary solutions. One of them, yx is equal to -1 for x belonging to real numbers. The other one, yx is equal to 1, x belonging to real numbers. Very nice. You can check easily that these guys are stationary solutions, or rather that are solutions as such. You take number 1, you differentiate as a constant function, you get 0, and you take number 1, put it here, 0. Wonderful, it works. How about here? Could it happen that the right-hand side gets zeroed for a specific choice of y? The answer is yes, we found it over here. Y is equal to 1. Yeah, that's the stationary solution. How about here? Is it possible that the right-hand side becomes 0 by choosing y? And the answer is yes, y is equal to 0. So, okay, I'm running out of room. So I'm going to borrow over here that there's stationary solution, or perhaps more. I have to be careful because there is a condition on existence. So there is actually two stationary solutions. One stationary solution has value 0 because this is what actually makes the right-hand side 0, the value 0 for y. On interval negative infinity 0, open. The second stationary solution has the same value, but it exists on the positive half plane. So one stationary solution goes along the x-axis and stops, and then another one starts. Two stationary solutions. I would see them in my slope field. Do I? Good question. Over here, that's the slope field. And okay, it seems to somehow be suggested by the picture that if I go along the x-axis, I will stay on the x-axis. Do I see it here in my list? I didn't ask for it. Well, perhaps I could add another one over here, just to show you that things can be done this way. So my starting time is -2, my starting value is 0. Let's see, and we can see the solution over there. Now, notice that Maple is complaining because sometimes when it substitutes things into this formula, division by 0 appears. So Maple feels unhappy about it, complains, that's life. But when Maple was drawing this stationary solution, it never got to the point 0, 0. So Maple didn't realize that there is a trouble there. But that's up to us, human beings, to recognize that there is a trouble and work it out accordingly. Okay, so that's the stationary solutions. And again, that's one of the questions I'm going to ask at the exam. When you get a differential equation, I will ask, sketch the slope field and tell me whether you see any stationary solutions. And you just look here, is there any y which makes the right-hand side 0? You write down the answer. For the autonomous equations, there is something special. For the autonomous equations, the fact that the behavior does not depend on the specific time, only on the elevation, so to speak, of the solution, it means that when you play with the initial conditions, you don't really care where you start with respect to time, only about the value. So the values are very important for autonomous equations. And therefore, people very often are not just talking about solutions, because a solution is a function and exists on some interval, for instance, on the real line. But they're talking rather about values which lead to a stationary behavior of a system. You set it up in a certain way and the system either changes or stays the same. For the stationary solution, do we see it here? No. For the stationary solution, the system stays the same. Here, if you start at 1 with your system, it stays at 1. It never changes. So the value is also important, and that's what is called equilibrium. So for this particular example, there are two equilibria. One of them is -1, another one is 1. So when I see them just as numbers, as settings for my system, then I call them equilibria. But when I see them as processes, I call them stationary solutions. Okay? It's not a big deal, but it's good to know what we are talking about. Okay? 2 points of view. In applications, especially when when people are talking about analysis, when they're analyzing systems, this point of view of equilibrium is quite popular. Okay, now we know what stationary solutions are. You have your system, you set it up in a certain way, and depending how you set it up at the start, it may start changing or it stays the same. So these are very special solutions, very interesting. And in applications, there is actually 2 or 3, depending how you count it, 2 or 3 types of stationary solutions. Let me give you a little example. And it's a very small example. I think this small example can be done over here. So, what you can see over here is a pendulum. Now, 20 years ago, everybody knew what a pendulum is. But since then, digital watches and mobile phones pushed out those good old grandfather clocks. So there are many people now here who actually never saw a real pendulum. So let me give you the substance of a pendulum. It's moving. And you push it and it starts moving like that, swinging left and right, left and right. Now, that's actually a system. It can be described using a differential equation. And in a few weeks, we will meet differential equations of higher order, and I will actually give you an equation which describes the movement of a pendulum. So the position of a pendulum, that's a solution of a specific differential equation. And there is one solution which is stationary, namely when the pendulum is just hanging. You leave it like that. Yeah, that's a stationary solution. There is another one. This one. These are both stationary solutions, but there is a fundamental difference between them. Imagine that you have this nice pendulum described by a differential equation, and somebody comes and bumps into it. What happens? Well, the position gets here, and it swings, 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 swings. Eventually, it comes to the center again. This is very nice. This is called a stable situation in engineering, and engineers really, really like stable situations. So this would be called a stable stationary solution or stable equilibrium. Definitely very useful in engineering. That's what we want. How about the other stationary solution? You take pendulum, you put it up here, you release it, and you would have to be really much better than me for it to stay up, actually. Usually there is some small disturbance, and then the pendulum just goes like that, and it never comes back. So that's the second type of equilibrium or a stationary solution, which is unstable. In engineering, biology, natural sciences, I mean everywhere where people study differential equations or use them to study systems, stationary solutions that are stable are very welcome. Let's say when you are designing a car and you are working on the suspension. When a car hits a bump, it starts undulating. So you have a stationary solution, the height of the car, the right height of the car. And the car goes, nice stationary solution, hits a bump and starts oscillating. Now what you really want is for this stationary solution to be stable. You want the car to slow down, to calm down, and then it goes like that again. That's the stable stationary solution, and actually designers had to work on it to achieve it. That's why they put dampers, not just springs. In the early carriages, they have just springs, and when such a carriage was going at speed and hit a bump, it started to oscillate, and if you were unlucky, this oscillation was actually increasing. So even before the airplanes came, the travelers were actually issued barf bags, because when a carriage, after hitting a bump, goes like that, you don't really feel well. So unstable stationary solutions are very bad. Unstable situations are bad. So can we look at our system, at our differential equation? We recognize the stationary solution. Can we tell whether they are stable or not? Well, let's have a look at the stability from the mathematical point of view. I have a constant function here. That's my solution. Let me put it like this. What does stability mean? Stability means that for a second somebody switched off this equation. You are running along this solution nicely, are feeling good. Suddenly somebody switches off this differential equation, moves you away, and then switches it on again. And the question is, do you get back to your original position? Well, perhaps not exactly, but in the limit. We would be happy with the limit. So stable means that you get back in limit if somebody moves you away from your stationary solution. This is what stability means. Unstable means that when you have your nice constant solution, you are running along, and then some outside influence bumps you away, and instead of returning, you go away. And when you look at the picture at the slope field, you can start seeing things, I hope. Over here, stationary solution 1 or equilibrium 1. If somebody moves you away, then the arrows suggest that you always go back. So my guess from the picture would be that this stationary solution, y is equal to 1, is stable. On the other hand, the stationary solution, y is equal to -1, is most likely unstable. If our common sense is worth anything. And the answer is actually, yeah, that makes sense. You move a little bit away from your stationary solution, and the arrows are quite clear about your future fate. You will never get back. So this instability, this is clear from the picture. What is not quite obvious is that this upper picture really gives you stability, but the good news is that for autonomous equations, it actually works like this. So, let me summarize it. When you get a differential equation, I can ask you for sketching the slope field, and you do it. I ask for stationary solutions, and you determine whether there are any or not. It could easily happen that there are no stationary solutions. That happens. If the equation is autonomous, then I'm going to ask you also about stability of those stationary solutions, and you just look at the picture and you write the answer. This is very simple. Now, I talked about 2 or 3 kinds of stability, depending how you count. Well, there are 3 situations, essentially. One situation when you have your stationary solution and the arrows go towards it. That's stability, obviously. Second situation, you have a stationary solution and the arrows go away. Unstable, quite clear. Third possibility is that the arrows go like that, or perhaps like that. Now, some people call this semi-stable. And if you like it, you can use it. I'm too lazy for that. For me, I look at it as an engineer. When I'm an engineer, I look at it and I can see that if I get, let's say, distracted a little bit in this direction, then I go back. So far, so good. But if I get distracted in this direction, then I go away, which is not nice. So for me, cases like that are also unstable. So I have just 2 cases. Stable, when the arrows go together, and unstable, which is everything else. Okay? So that's how easy it will be in the course. Some people, they have semi-stable. If you put it in the answer on my test, I will be okay. I will take it. Okay? But as I said, I'm going to ask this question only about autonomous equations. Why? Well, let's have a look at here, in this picture. I have a stationary solution, y is equal to 1. What happens if I'm moving along this solution and somebody kicks me away a little bit? Well, it seems that I will be going back, but suddenly I'm going away. So what does it mean, really? Over here, stationary solution, y is equal to 0. I'm going along the stationary solution, and suddenly it stops. What does it mean? I don't know. I mean, this is really bad. So for the stability to make sense, you want to be able to go all the way to infinity. That's the first thing. And if your equation is not autonomous, then you may have trouble. Here, there is just one trouble. But it can easily happen that there are infinitely many troubles. And you can even go to infinity with your time. So it doesn't really make sense to talk about stability at all. For these 2 examples, it actually does make sense to talk about stability when you are here, near infinity. You can ask, what's happening here? In this case, I would look at the picture and I would say, okay, if I'm here on my stationary solution and I move a little bit away, then those arrows will pull me away even more. So I would say that this stationary solution is unstable. And I think it's okay. However, why don't I ask questions like that on a test? Because you may end up with a different picture, this picture. Here, near infinity, I'm running happily along my stationary solution, y is equal to 0, this one, for positive times. And some influence moves me a little bit away. And the arrows suggest that whether I move up or down, I should always go back towards the stationary solution. But the fact that I'm going back does not guarantee that I will actually get back. Let me show you a little picture here, enlarged picture. This is y is equal to 0, stationary solution. Some outside force, for a second, influences your situation. So in this range, the differential equation for a while does not work. The force moves you away, and now the differential equation kicks in again, and we are asking, okay, what's happening? Now, according to the picture, the solution should be decreasing, decreasing, decreasing. So the solution is decreasing, decreasing. But what if it levels off too soon? What if there is an asymptote, typically called capital L in calculus, and what if the solution goes to this asymptote instead of going back to your stationary solution? Could it happen? And the answer is yes. So if you have a general equation which is not autonomous, that's the key thing. If your equation is not autonomous, then having arrows going towards each other does not guarantee stability. You simply don't know. So for equations like that, if you want to investigate stability, you have to do much more work. This is really, really advanced stuff. Okay? So that's why I'm not asking about stability for general equations, because you may easily find yourself in a situation when you cannot answer, because you don't have the tools. So I will always ask only about autonomous equations, this stability question, because there, if you have concentric arrows, you are sure that you get stability. That's a special feature of autonomous equations. Fortunately, in applications, I talked about it, typically equations are autonomous, so this kind of analysis can be done, and I've seen it done by people in different areas. For instance, I've seen people studying stability of fishing systems in the Atlantic. The American Oceanographic Institute, something like that, I found on their webpage, interesting analysis of stability of solutions, things like that. So this is really applied stuff, used in applications, used in real life. Okay, so that's about it. What we just did is we took a differential equation, we learned how to sketch the slope field. Computer can do it better, by the way. That's another story. We learned how to identify stationary solutions. And if your equation is autonomous, then it makes sense to ask about stability, definitely. Sometimes, if you get lucky, you can also reach some conclusion about systems which are not autonomous, like this one. I really see instability of this stationary solution here in the picture. So I think I can say this, but I'm not going to ask on a test, okay? So now we know what stability means, and perhaps we can decipher the definition. So here we go. We have a first-order differential equation, which is autonomous, so there is no x part in the right-hand side. And we have an equilibrium, which is the value which makes the right-hand side 0, identically 0. And it's also, as a solution, as a function, it's a stationary solution. So here we go, x, y, and here is y naught. That's the stationary solution. And the definition says that this equilibrium, or this stationary solution, is asymptotically stable, and I will just say stable in this course. There are some other type of stability, like Lyapunov stability, but we will not look at them here. So I will just say stable. So the solution is called stable, the equilibrium or stationary solution, if, let's see, there is the, let's skip that part. Let's look at the second paragraph. If some solution gets close to our equilibrium or stationary solution, and this D tells us how close we are allowed to go, then the solution must automatically go in limit to y naught. So there is some strip, and the width of this strip is D. And if some solution gets into this strip, then in limit, it must go to our stationary solution. Okay, let's check that it really says so. So there must be some D positive, so that's this strip, so that every solution of our equation which drops into the strip, that's the inequality, yx minus y naught is less than D, then in the limit, it must go there. So this really captures the meaning of stability. Why is this D in the picture? Well, here is a simple idea. Imagine that you have a leaf spring. So it's actually a strip of steel. You hold it, and the end point, that's the position. That's the stationary solution. If you hold it like that, it's definitely stationary. Now, if you bend it a little bit, it will go back. Stationary solution, which is stable. Wonderful, stability. But if you bend it too much, it just bends hard and it stays there and it will never go back. Yeah? So that's what happens when you exceed this D. You are no longer guaranteed that it will return. Something else can happen. Okay? So that's the meaning of the definition. Before we move on, I still owe you one. I've been showing you slope fields, at least the way Maple sees them, for these first two problems. And I also asked Maple about the third one, which is autonomous and interesting. So let's see whether Maple agrees with us. Slope field, our picture, yeah, they do agree. Let's have a look at some solutions. Yeah, this seems to make sense. I can see the stability. for the y is equal to 1 solution. Down here we can see the stationary solution y is equal to -1 and it's unstable. In the middle strip you can see this thing I've been talking about, that when you start at a certain elevation with certain value of y, then it doesn't really depend where you start, because the curves, they are of the same shape. They're just shifted, okay? So everything fits. That's very nice. And that's essentially it for this. That's the main part of this lecture. We learn how to do sketches of slope fields. We learn how to determine stationary solutions, how to determine stability, instability for autonomous equations. And that's it for the exam. I call this chapter Analyzing Solutions of Differential Equations. Analyzing means getting as much information as you can from the equation itself. And this is the part that I'm going to ask about on the test, but there's actually more to it. So if you are curious, you can stay a while, a few minutes, and I will show you how you can actually extract more information from such an equation. I think you will enjoy it. Let's look at it. Okay, we go back to our example. Y prime is equal to 2x times y minus 1. And let me focus just on positive axis. So what we found so far is this picture. There is the stationary solution, y is equal to 1, and the solutions go like that if they are above or below. So there are three distinct families of solutions. The stationary solution 1, increasing solutions, decreasing solutions. What does it mean? Well, it means that if some solution is not equal to 1, then it must have a limit at infinity. And that's an important consideration when you are analyzing solutions. Will there be some oscillation happening? The answer is no, because the solutions are monotone. Every monotone function must have a limit, finite or infinite. We don't know. So that's a good question. Is this limit infinity, or perhaps negative infinity, or is it some number? Now, to see that, I'm going to do a little trick. This equation gives me information about the first derivative, which means monotonicity. What happens if I differentiate again? On the left, I get y double prime. On the right, I have to take into account that y is in fact a function. So this is a product rule. I differentiate the first part, and I copy the second one, and then I copy the first one, and I differentiate the second one. And when I differentiate, I get derivative of y. And I could keep it like that, or I could perhaps substitute from the original equation for y prime. And when I do that, I can simplify my life by factoring out 2. I factor out y minus 1, and I get 1 plus 2x squared. And that's a formula for the second derivative. Well, let's have a look at it. I can use similar reasoning. On the right, I can see a function of 2 variables, which describes concavity of my solutions. Now, are there any dividing curves? Well, this factor is always positive, so it will not really play any role. Number 2, always positive. So everything is decided by the y factor, which has a change of sign at 1. So again, here is 1. And if we are in the upper part, then y is more than 1, positive, positive, positive. Positive here, which means concavity up. If we are in the lower part, y is less than 1, this whole thing is negative. Negative second derivative means concave down. Concave up, concave down. So that's the picture for the concavity of our solutions, and that's the picture for monotonicity. And when we put it together, we can see that the solutions should be going like that and like that. And let's go back to the original question. Is the limit finite or infinite? The answer is infinite, definitely, because when the function is concave up and increasing, it cannot level off and have a finite limit. This can be proved mathematically, but I think it's so obvious that you will trust me on this one. Okay, increasing, concave up. Increasing, concave up. if I wanted to have a limit, a proper limit, finite number, I would have to be concave down, definitely for an increasing function. But this is forbidden. So based on this information, I can conclude that limit x going to infinity yx is infinity for y greater than 1 and negative infinity for y less than 1. And of course, the limit is equal to 1. For y is equal to 1, that's the stationary solution. We extracted more information. Good question is, how quickly does the solution go to infinity? This is sometimes very important. Does it go to infinity relatively slowly or really fast? Typically, we compare. So, what can I say about the limit of my solution when I divide it by x? Well, notice that when x goes to infinity, then x itself goes to infinity, and the solution also in absolute value, so it's plus or minus infinity. The important thing is that regardless of plus or minus, this is an indeterminate ratio, and we are entitled to use L'Hopital's rule. So I'm going to use it. Limit x going to infinity, y prime divided by 1. So I am actually looking at the limit of y prime x going to infinity, which is limit x going to infinity of, and I substitute from the differential equation. Here we go again. And then I look at this expression. When x goes to infinity, then this part is obviously infinity. And the y minus 1 part can be handled from here because I have information. So there are two possible answers of interest, although there are actually 3. When y is equal to 1, then this is just 0. But when y is greater than 1, then the answer is infinity. And when y is less than 1, the answer is minus infinity. Either way, when you ignore the stationary solution, it's important, but now we are more interested in the other guys. Those other guys, they go to infinity, and they go there faster than straight lines. So it could be some higher power, like x squared, x fourth, and so on. So what can do, one can look at limit y over x squared and play the game again, L'Hopital's rule and so on, and this information is then used in the solution here, and one can find that again it's infinity. And using induction, one can actually show that this function yx, the solution to my problem, goes to infinity faster than any power. And that's the moment when you start getting suspicious. Okay, could it be exponential, something like that? So even without knowing the solution, we actually know that it's the exponentials, the solutions. We solved it when we are doing separation, okay? But just pretend that we don't know how to solve it. From this analysis, I not only get a good picture of the situation, but I also start this suspicion that my solutions are going to infinity really fast, which is usually not pleasant in applications. So that's an important piece of information. So that's the end of the bonus. And that's the end of the chapter, analyzing solutions of differential equations if I cannot solve them. There is still one key question unanswered. So see you in the next video. Hello. Okay, once more. Hello. In applications, a differential equation typically describes the behavior of some system, or more precisely, the behavior of some quantity that we are interested in. Hello. Typically, no. Again. Hello. In applications, we use differential equations to capture the behavior of a system, or more precisely to some again and again. Okay. Here we go. Hello. In applications, we use differential equations to describe some system or a quantity that we are interested in. And this can be done, for instance, by sketching or drawing Hello. In applications, we use differential equations to describe the behavior of a certain system that we are interested in. And we want to gain... No. Okay. It's early morning. Hello. In applications, we are using differential equations to describe the behavior of different systems that we are interested in. And we are hoping that this differential equation will help us in understanding what's going on. Okay, let me try one more. It was almost good. I almost liked it. Hello. In differential equations... Okay. Hello. In applications, we use differential equations to capture the behavior of some system that we are interested in. And having this differential equation, we can actually hope to find also its general solution, which is wonderful because we can use it to gain information. For instance, if we are interested in some specific instance of this system, of this proceedings, of this process. Okay, process. Okay, let me try it again.